Part C. The circuit below consists of 8 resistors, each with resistance R. So let's just draw that out. There we go, and we've got A there, we've got B, D, C, O, and we've got current coming in there, and we've got current coming out there. In fact, it's the same current, and it's got to be the same current because we can sort of draw a box around that. Consider this as just one component. Therefore, Kirchhoff's first law, current in, has got to be current out. Okay, explain why B and D are at the same potential. Okay, so what that means, at the same potential, so if we were to put a voltmeter across there, we're going to record 0 volts. Now, from symmetry, that's pretty clear. But I think we need to write more than just the word symmetry on the answer. Well, what we know is, well, let's consider the potential there. Say that's, well, we may as well consider it as being 0. We can put our 0 anywhere we like. Let's put it there. So we'll say VA equals 0. Then VB equals, well, what do we lose going there? So if we say that we have current, let's call it small I, it's obviously not the same as big Y. So VB, and we'll call that small r, is going to be VA minus IR. We're losing that potential as we go through that circuit. VD equals VB minus IR. Now the key thing, these I's are the same because of symmetry.
Is that also VA minus IR then? Or?
Sorry, yeah, you're right, VA minus IR. So that's just minus IR. Minus IR. We can see, because all these R's are the same, we can just, we've got a line of symmetry there, so we can just flip that over there. So the current going there has to be the current going there. It might be quite hard to work out what that current is, but we know it's got to be the same. Therefore, so that is just saying VB equals VD. Calculate the effective resistance between A and C. So that means, okay, so if we were, I've drawn the screen loop around it, so if we were to take that circuit and say, what is the resistance between there and there? So if we were to place that by an equivalent resistor, what would we get? Now, I would not start trying to use your formulae for resistors in series and parallel at this point, because this is a rather complicated circuit. I think you would get in a complete mess, and I don't think you would get it out anyway using just your resistors in series and parallel formulae. You need to be a little bit smarter than that. So let's just, again, followed by symmetry, just think, well, what are our currents and things in here? So let's say we've got a current I flowing that way. Now, by symmetry also, we looked at this point here, we've got I that way, I that way. We've got a line of symmetry this way. So if we flip A onto C and change our currents round, current going the other way, we would have I. So we know that we've got to get current I that way and I that way, just from the symmetry side of it. By symmetry, current B to C equals I, D to C equals I. So, what we want to know, we want our resistance is going to be our voltage between A and C, voltage between A and C, divided by our current that flows between A and C, which is equal to I. One is VAC, so Kirchhoff's second law. Go from A to C, see what we get in terms of currents. So we can go this way, we can go to there, to there. Kirchhoff's second law from A to C, voltage drop equals I times R. So that one's for A to D plus I times R. D to C. So we've got 2 IR is our voltage VAC. We know R. So our resistance is just 2 IR divided by our total I. We know that. So what we need to do is get some cancellation going there. So what is our total current in terms of our I? Now that needs to have a quick think about, because our total current, I is I plus whatever flows through here. Now, what is this one here? Let's call that I tilde. So that's 2IR, and I is 2I, which is that one plus I tilde. What is I tilde? So we're going to need to think about potentials there.
This is the
Well,
trick,
it's
isn't
going
it?
to be, this is going to be the same potential as that, isn't it?
I think so.
Yeah, because, have a think about
This goes back to symmetry again. doesn't it?
these resistors here. You know, does the current flow that way or that way through those resistors? And if it were to flow that way, you're saying that this potential is greater than that potential. But, is that right? Why are we saying it's living at 0 in the middle? It's the same. Oh yeah. I see.
Yeah, as a less mathematical approach, more by allegory, I guess, if you're considering water flow, those two resistors in the middle are kind of dead pathways,
Of
aren't they?
course, yeah, they are.
You wouldn't have water flowing in either direction on them because the path of least resistance or the...
Yeah.
Which it's a little bit hard to nail down an explanation, I feel, but...
I was thinking, look, we know that potential is the same as that potential. We've done that.
Does it tell us anything more than that the flow will be either both towards the centre or both outwards?
Both away, yeah.
Or does it tell us that...
Yeah, but you see, we know from symmetry, the potential here is going to be half the potential A to C.
yeah, there we go.
So we know that V AO is half V A to C.
This gives us a mathematical...
But V A to D equals half V A to C because we can go IR, IR.
That's the key.
Therefore, the potential at O equals the same as potential D, the same as potential at B, so no currents in star and star.
Which means I tilde is also I.
Which means I tilde must be I, because the potential here is the same as potential here. There's R there, so I tilde must be I. So I tilde equals I, and we're jumping around here, but R back from here equals 2IR over 2I plus I tilde equals 2IR over 3I. So that is 2/3 of R.
Cool. And you could check that using your parallel and series resistance formula by just getting rid of those two star resistors as well, don't you?
So if we were to do that, then that's a rather easier circuit to analyse, because what we've got then is we've got a loop which has 2R, that's that one around there. We've got a loop that's 2R down the middle, 2R down the edge. So we've got 3 lots of 2R in parallel. So the 3 is going to give you the 3rd on the bottom, and the 2 is going to give you the 2 on the top.
Nice.
Easy when you think about it. Getting there, not necessarily quite so straightforward. Okay, part D. I don't think this has anything to do with that one.